Hi folks, ever wondered how machine learning make decisions under uncertainty? So welcome to the world of Markov decision processes. So here today we will learn about how robots will make decisions, and I'll tell you about the formulas and basic definitions and how we will deal with the Markov decision process and how to understand this. So we'll deep dive into that. So at core MDP is a process. So in this we will be learning about simple way components of MDP form model and understand its formula, also how we will be getting the different types of decisions and policies. So coming to the next slide, it is a definition of framework. So this framework is used to make the reinforcement learning and decisions in the environment in which the robot was introduced. So generally Markov decision process is a stochastic dynamic program and or stochastic control of problem, and is a model for sequential decision making and where outcomes are uncertain. So this is also a framework where partly the outcomes will be random or partly controllable. So we can use it in different places and like different industries like ecology, economics, healthcare, telecommunications, and reinforcement learning. And this reinforcement learning uses the MDP framework to model the interaction between learning agent and its environment. So in this framework, the interaction is characterized by states, actions, probabilities, and rewards. So the name comes from its action to Markov chains, and it was given by Markov guy. So we will discuss about him soon. And this Markov is this chains, and whatever chains we use for the decision, and this has later propagated into Markov decision process. So he's who is the scientist for this decision making for the Markov guy. So he is Andreevich Markov. He's a Russian mathematician, and his primary subject of research was Markov chain, and he was also a chess player. And he was also a mathematician, and he was good at constructive mathematics and recursive function theory. And he was born on 1856 in Russia. Okay, so and what are the parameters in this MDP? Nothing but Markov decision process. So in this we have something called states and actions, probabilities, and rewards. So these probability states, what is a state? So when making a decision, you need to think about how actions will affect the things. The state is the way world currently exists, and the action will have effect on changing the state of the world. So if we think the set of every possible way the world could be, then this would be the set of state of the world. So each of the state would be in different state in MDP. So let's understand in a common way. Suppose if a robot is in at a starting point, then it is in the present state, and if it moves to the next step, or it moves from its position to a new position, then it is a next new state, and it moving is called action. And the probabilities of, I mean, like if a robot is placed in the center of a room, it can move forward, backward, left, or right. So we don't know in which direction the robot moves. It completely depends upon its whatever algorithm we have given. So that is nothing but probabilities. And rewards are the gives whatever we give for the robot's decision making. So suppose it moves towards the direction of the destination, so we reward it in a positive way. If it moves away, then we will give negative rewards, like that, so that the robot also will understand how to move and in which direction we have to move. And the discount factor is something which is used to calculate the rewards and policies. Okay, and immediate rewards. So the solution of MDP is proposed by Markov guy, and these are the important parameters which are in the MDP. So these are the formulas which are there in the MDP. So we will learn how we have to interpret this. So here we can see the robot will start from this point and will exit here. So it can move in different paths. I mean, like it can start from 1 to 2 and 2 to 3 and 3 to 4 and 3 to 4 to 3 and 3 to 5. thing is, it has to move through each and every node. Okay, so it has to move through each and every node and take the reward that is given by the node, and it has to take the best decision, and it have to take the best path to go to the destination. So here it starts from 1 and then it moves to 2. The reward is -5. So it moves from 2 to 1, then the reward is -10. So if the robot is at position 2 and it moves at 3, the reward is -1. If it moves from 3 to 2, the reward is -5. So likewise, the rewards are awarded, and we use the formulas to calculate all the rewards. In this also, there is S state R for reward. So if S is 0, then the starting point is, just assume this is a starting point. So from here it will move towards right, and it is going through all the boxes and then reaching the end of the box. Okay, so here S is equal to 0, it is the initial state, and R is equal to -0.04. So this is the reward in initial position, and next S is equal to 1, R is equal to -0.04. So the reward is constant throughout the journey that our robot takes. So S is equal to 2, then R is equal to this one, and it has to reach to this destination. This is S is equal to 3. There are different types of moves that a robot can make in this. Like, suppose if it is in S box, it can move to 1 box also, and it can move it to 4 box also. We don't know which direction it moves, because MDP is something which is based on probabilities. There is number of probabilities that it will move right side or it will move towards downwards. Okay, so here also in box number 6, if it moves right side, then it is in the wrong position, and if it is towards the upwards, then it is right position, and the reward is -0.04. And here you can see the reward is 1.0, and here the reward is -1.0. So the reward is higher here. That means it is wrong position that the robot should not travel. So all these boxes which are in white color are having the rewards -0.0, means that if the robot travels in this direction, then there is no impact. I mean, like, all are having equal rewards if you travel during this direction, and if you reach to the right point, then you will get one reward, and if you will reach the wrong point, then you will get negative reward. So by this, our robot will understand that this is the optimal path, this is not optimal path, this is the longest path, and it is a wrong way to for us to understand. I mean, like, the human will understand it in a better way. And here we can see the formulas here, V of S and pi of S. What is V of S and what is pi of S? So here V of S is nothing but the value of S, and pi of S is policy. So to calculate the optimal policies, okay, so the value update, the V of S is nothing but the summation of rewards. Okay, so throughout this path, in this you can see here I have got 1 to 2 I will be traveling, and 2 to 3 I will be traveling. So the rewards I should calculate at some point of time, and I should get the rewards. Like, I will get the rewards, but I have to calculate the sum at the end. So that is done in this formula. So I will calculate the rewards that are obtained by one path, and pi of S is the policy. Policy is nothing but, we can say that the best way to travel by one way. Okay, the value update and the policy update, so these are repeated for all the states, and until there is no further change takes place. And pi will contain the solution, okay, how to move to the best how to destination, and VFS contains the discounted sum of rewards to be earned, okay, by following solution at that particular state. And V of I plus 1 is nothing but the value iteration, which is nothing but the backward induction. So here pi will not be calculated, is not used. Instead, the value of pi of S is calculated with V of S whenever it is needed. So substituting the calculation of pi of s in the calculator of v of s, so we'll get this formula. So pi of s we will substitute in v of s, and then we will get the formula in this formula, and where I is the iteration. So this we have the solution for MDP. So here the standard family of algorithms to calculate the optimal policies or optimal paths for the robot for finite state and action. So MDP required storage for two arrays indexed by state of value v and value s and policy pi, so which contains actions. So at the end of the algorithm, pi will contain the solution and v will contain the sum of rewards end by following solution from state s to s dash. So algorithm has two steps, okay. So one is value update and other one is policy update, which are repeated in some order. So for all states until no further changes takes place, I mean like it should travel from all the paths from A to B that is specified by the user. So we should get the optimal policy and maxima the state value under using the older estimates of these states. So the v of s is nothing but here the value, so it will give the summations of all the possible rewards and probabilities that are traveled by the robot, and pi will give us the policy update which is having the path. So it depends upon the variant of the algorithm, that is nothing but gamma here. So as long as no state is permanently excluded, we will get the optimal solution in this. And v of I plus 1 is nothing but the iteration actually, so value iteration. So this is nothing but v of I plus 1 is nothing but the next state, and I is the iteration number. So v of 0 as case of value function, so it iterates repeatedly from s for all states of s until v converges from left side is equal to right side. So the value iteration, the pi function will not be used here. The pi function is substituted in v of iteration. So this is nothing but v of I plus 1 is nothing but the next state, and I is the iteration number. So v of 0 as case of value function, so it iterates repeatedly from s for all states of s until v converges from left side is equal to right side. So the value iteration, the pi function will not be used here. The pi function is substituted in v of s, and then we will get this formula. Okay, so the next one is the Bellman's equation. So this is Bellman's expectations equation for Markov reward process. So the Bellman's equation gives standard representation for value functions. So he said about only value functions, not about policy functions. So the value there is immediate reward, that is nothing but r t plus 1 and discounted of the next state, future state. So he have calculated the formula for this, and where v of s is present state, r t plus 1 is future state, gamma is nothing but the discounted factor as we already know, v s t plus 1 is future state, s of t is present state, and this is the equation to calculate the value of summation of rewards that we will get. So if we move from state, and we'll have the value of s, and when we move from one state to other state, we can make the next state as s dash. So this is s dash, and the formula is calculated. So this is Bellman's expectation equation. So test experiment with an experiment. So you can write code for this Markov decision process, and you can have it, and you can design it, and you can store the data in form of graphs, diagrams and maps, and you can do the analysis on the data which was given by the robot while traveling from source to destination. And I hope you have learned something new. Please subscribe and let me know if you want more detailed video on this, so that we can proceed with more videos on this topic. Thank you.